Okay, excellent. Welcome everyone back to another DyMap seminar. So today's speaker is someone very familiar to all of you. So this is Sayan Bhattacharya from University of Warwick. Sayan has been at Warwick for the last 4 years, and he has a very excellent track record of contributions to dynamic graph algorithms. And in particular, this work which receives the Best Paper Award at iCalc this year in the track A. So Sayan today will talk about his paper with his student Peter on deterministic rounding of dynamic fractional matchings. So Sayan, whenever you're ready, the floor is all yours.
Thanks, Ramanujan, for the introduction. Can you see the screen clearly? Okay, great. So this is joint work with my student Peter Kiss. And during the talk, if you have any question, feel free to use the chat. And Ramanujan has kindly agreed to just alert me to any chat message that you might send. Okay, so let's start. Interesting. My laptop, this is, just give me 1 second. This is a problem I was having even a few hours back. My laptop has completely hung. Hello?
Yeah, but we can hear you. Yeah, okay.
Okay, right. Okay, so let's start again. Hopefully this, yeah, this is fine. Good. So let me start by gently introducing the area of dynamic algorithms. Take your favorite optimization problem and consider any algorithm for it. Suppose on a given input I, it produces an output O. Now suppose the input changes slightly by means of an update. And after this update, we need to recompute the new output O plus delta O. What should we do? How to proceed? There is a trivial answer to this question. Simply run the same static algorithm from scratch on the new input. But can we do something significantly better? Instead of recomputing from scratch, can we somehow use the information we already have to speed up our update time? And this is the question that lies at the heart of almost all dynamic algorithms problems. And you can see that you can ask this question in the context of any optimization problem. In particular, in today's talk, we will be considering the maximum matching problem in the dynamic setting. So recall that a matching in a given input graph is a subset of edges that do not share any common endpoint. So for example, this set of red edges on the graph on the left-hand side form a matching. And our goal is to maintain an approximately maximum matching in this dynamic setting. And you can think of it as follows. Matching is one of the most fundamental graph algorithmic questions, and we are asking what happens to this problem in presence of dynamically changing inputs. Okay, now let me define the problem a bit more precisely. We have an input graph G with n nodes that keeps changing via a sequence of updates. And our dynamic algorithm is supposed to store a matching M of this input graph in an output memory. So an update inserts or deletes an edge in the input graph. After this update, the algorithm goes ahead and makes some changes in the matching that it is storing in the output memory. This is all that happens. The update time will be the time taken by the algorithm to handle an update. And our goal is to design a dynamic algorithm with small update time and small approximation ratio. And note that there is a trade-off between these two objectives. So for instance, if you don't care about the update time at all, you can always recompute from scratch after every update and you get an approximation ratio of 1. On the other hand, if you don't care about the approximation ratio, you can just maintain a single edge as a valid matching, and you can have very fast update time. So we want to minimize both these two quantities simultaneously. And throughout the talk, I will only be focused on amortized update times. So to be precise, when I say that our algorithm has amortized update time log n, let's say, it just means for any sequence of t updates, it takes total time t log n. So on average, the update time is log n, but there might be some updates where the algorithm takes a long amount of time. So this is the setting. And now, before proceeding any further, let's start with a very naive dynamic algorithm for this problem. And the algorithm will just maintain a maximal matching. So recall that maximal matching is basically the output of the greedy algorithm for computing a matching. So specifically, a matching is maximal if and only if for every unmatched edge, at least one endpoint is matched. So on the left-hand side, you can see a maximal matching highlighted in red, because if you take any blue edge, any unmatched edge, at least one of its endpoints will be incident on a red edge. That's why this matching is maximal. And it's very well known by a simple proof that any maximal matching has approximation ratio at most 2. So the size of the optimum, the maximum matching is at most 2 times the size of a maximal matching. And now suppose we just want to maintain a maximal matching in this dynamic setting. What do we do? The algorithm is simple. When an edge gets inserted, suppose UV, this edge gets inserted, you just check if both its endpoints are unmatched. If yes, include it in your matching, and this takes constant time. On the other hand, suppose an edge gets deleted. If this edge getting deleted did not belong to your initial matching, then you don't need to do anything else. The previous matching will remain maximal. Otherwise, if the edge getting deleted was actually matched, you delete it from your matching, then you visit its 2 endpoints, and for each of its endpoints, you try to match it to any free neighbor available. So you are doing a linear scan of the neighborhoods of these 2 endpoints. And at the end of this procedure, you can be sure that you end up with another maximal matching. What is the time taken to handle a deletion? It's proportional to the sum of the degrees of the 2 endpoints, because you are making linear scans of their neighborhoods. And these degrees can be as large as n. So the time taken can be as large as big O of n. Now, this is a very simple algorithm, and this is our starting point. The question is, we have already seen how to maintain a 2 approximate maximum matching, that is a maximal matching in linear update time, linear in n update time. Can we do significantly better? This is our starting point. And the ultimate goal in this area, or in this topic rather, is this. Can we design a 1 plus epsilon approximation dynamic matching algorithm that runs in polylog n update time? And we are still very far away from this goal. And this polylog n update time, this threshold is important because if you think about it, in order to specify an update, insertion or deletion of an edge, you only need order log n bits in an n node graph. So when we ask for polylog n update time, we are asking for update time that is polynomial in the size of the input to our dynamic algorithm. And that's why for many dynamic graph problems, the holy grail ultimately is to achieve polylog n update time with as good approximation ratio as possible. And just to complement this open question, it's known that you cannot get exact maximum matching in polylog n update time, subject to some strong conditional lower bounds. Okay. So let me now spend a bit of time reviewing the past literature. Basically, over the past decade, a lot of work has happened on this problem. And primarily, it's because there are many different parameters to optimize. So for instance, you can consider either the fully dynamic setting, allowing for both age insertions and deletions, or you can look at more special cases where you only allow for age insertions or age deletions. Similarly, you can look at amortized update time or worst case update time. You can look at bipartite or general graphs. You can trade off the approximation ratio. You can think about randomized versus deterministic algorithms. You can think about the graph being weighted, unweighted. There are so many different parameters. Each gives rise to a different setting. Now, here is a very crude summary of the state of the art on this problem, keeping in mind that there are quite a few papers I'm missing out on, because there are literally probably 20 or 30 papers on this topic right now. So here's one way to summarize the state of the art. And it revolves around this approximation guarantee of 2 that comes from this maximal matching, which gives 2 approximation. If we want better than 2 approximation, then currently only subpolynomial update time algorithms are known, and I have listed 3 of them here. And this is fully dynamic. The second strand of work would just focus on polylogarithmic update time in the fully dynamic setting and are happy with randomized algorithms. There, quite fast algorithms are known with even constant update times, but the approximation ratio is 2 or 2 plus epsilon, and they are all randomized. If you want fully dynamic deterministic algorithms in polylogarithmic update time, you can get 2 plus epsilon approximation, but the update time is actually a very large polylog, log to the power 21n, and it's quite complicated. Finally, you can focus on either decremental, deletion-only setting, where you have efficient guarantees in bipartite graphs, and you can also focus on insertion-only incremental setting, where you also have very good guarantees even for general graphs. Now, if you look at this slide, one thing that you will observe after staring at it for 2 minutes is that quite a few of these state-of-the-art algorithms here are randomized. I have highlighted them here in blue. And it so happens that they are actually randomized for the same reason. If you just look at the reason why they are randomized, the reason is the same. And the question one can ask is, can we get around this barrier? Can we tackle the reason for which these algorithms are randomized and de-randomize them all at one go? And this is the main contribution of our paper. So in a nutshell, using a single framework, we de-randomize multiple existing algorithms for dynamic matching. And it is important to note here that de-randomization in itself is an important research agenda in dynamic algorithms. This applies to many different dynamic problems, and especially because we currently don't know of any technique for dynamic lower bounds that can give us a super polylog separation between deterministic and randomized update times. And this is in sharp contrast to some other areas like online algorithms, where it is very well understood that for many problems, if you don't use randomization, you are going to get a significant hit. Okay, so this is a brief summary of our contribution. Now, in order to explain this contribution in more detail, I need to make a detour. So for a few minutes, I need to spend time motivating the concept of dynamic fractional matchings. So let's proceed with it. So what is a fractional matching? It's basically the LP relaxation for matching. So you get a graph, you have to assign values to edges, and these values can be fractional. They need to lie between 0 and 1. And if you look at any node, the sum of the edge weights on that node should sum up to at most 1. So for instance, on the right-hand side, you see this triangle. If you assign a value of 1/2, 1/2 to every edge in this triangle, you get a fractional matching, because if you look at any node, the total weight it receives from its incident edges is 1. So this is a fractional matching. And this is a generalization of integral matching, because for an integral matching, you are just assigning 0, 1 weights. So on top, you see an integral matching with the red edge being matched, that getting weight 1, and the other edges getting weight 0. And this is a notation that I will use throughout this talk. So please familiarize with yourself with this notation. W of E will denote the weight assigned to an edge, and W of V will denote the total weight received by a node from all its incident edges in a given fractional matching W. Okay. So the size of a fractional matching is just sum of the total weights assigned to all the edges. So this will be denoted by size of W. Again, I will be using this notation for the rest of the talk. And the size of the maximum fractional matching, let's say it's mu f of G. F denotes for fractional. And it's known that in bipartite graphs, there is no integrality gap. So mu G here denotes the size of the maximum integral matching. This is the same as the size of the maximum fractional matching in bipartite graphs, whereas in general graphs, they differ by a factor of at most 3/2. Now, here is an important caveat. If you wish to understand the main conceptual message behind this paper, for the rest of the talk, ignore the integrality gap. So just pretend that there is no integrality gap, and basically we are working on bipartite graphs. Okay, that's where the conceptual meat of the talk lies. Okay. Now, why do we care about fractional matchings? Well, look at this very simple instance, dynamic instance. So the adversary ensures that the input dynamic graph remains almost d-regular, meaning that every node has degree between 1 minus epsilon times d and d. And let's say d is some polynomial in n, say d is root n. And now adversary keeps inserting, deleting edges in this graph subject to this condition that it remains always almost d-regular. On this input instance, suppose I now ask you to maintain a large integral matching. What can you do? A priori, it's not at all clear what to do here. But if I now ask you to maintain a large fractional matching on this instance, the answer is trivial. Why? Because all you will do is you will set a weight of 1 over d to every edge. And this will imply that if you look at any node V, it has roughly d edges. Each of these edges have weight 1 over d. So the node receives weight very close to 1. So all these nodes are almost tight. And this is a near maximum fractional matching. So this gives you 1 plus epsilon approximation to maximum fractional matching, and you can maintain this in constant time. So what this tells us is that fractional matchings are inherently more stable than integral matchings because they are putting very small fractional values on these edges. If the adversary deletes an edge, it cannot hurt you too much. It cannot hurt the algorithm too much because the objective maintained by the algorithm doesn't drop too much after an edge deletion. And that's why in the dynamic setting, it should be useful. It should be much easier to maintain fractional matching. Okay, so there is actually a long line of work in dynamic algorithms for maintaining fractional matching. I'm just citing 3 of them here. The specific details here are not relevant, are not super important, but all you can just assume from this is that we know how to maintain fractional matchings very fast, quite well. And in particular, all these 3 algorithms are deterministic. And 2 of them run in very fast polylog update time, and 1 runs in arbitrarily small polynomial update time. Okay, so for dynamic fractional matchings, we can get deterministic algorithms with very fast update times. That's the take-home message. Now, it so happens that many, but not all, dynamic matching algorithms in the literature follow a common template. And again, I just emphasize it's not all algorithms, but I will say quite a large number of them. And now let me spend a few minutes explaining this common template. And the template is this. You take a dynamic graph you feed it into a dynamic fractional matching algorithm. It outputs a fractional matching, and then you come up with a dynamic rounding scheme that rounds this fractional matching into an integral one without losing too much in the objective. Now, the key part here is the rounding step. How does this rounding step work? First, recall something we observed in the beginning of the talk, that we can maintain a maximal, that is 2 approximate integral matching in order d update time deterministically, where d is the maximum degree in the graph via the naive dynamic algorithm. Now, there is a very well-known result in this area by Gupta and Peng from 2013, which says that if the graph has bounded degree, if the graph is sparse, then actually we can maintain 1 plus epsilon approximate maximum integral matching in order d update time. So it just takes a leap from this naive dynamic algorithm and improves the approximation ratio to 1 plus epsilon. And the update time remains order d, where d is the maximum degree. Now, given this subroutine for maintaining dynamic matchings in sparse graphs, a dynamic rounding scheme basically consists of 2 steps. The first step is sparsification. So the dynamic sparsification algorithm takes as input a dynamic fractional matching and outputs a sparse subgraph G prime. And it's sparse because it has low maximum degree D. So D is polylogarithmic here. And this sparse subgraph admits another fractional matching W prime on it, whose size is close to the size of the initial fractional matching W. This is what sparsification does. So it sparsifies the graph, preserving the size of the fractional matching we started with. And now that you have this sparsified graph, you just feed it into this Gupta-Peng algorithm, which runs very fast on sparse graphs, and it outputs an integral matching M prime in this sparsifier. And now again, just assume that the graph G is bipartite, then this M prime is a near optimal integral matching in G prime, which is the same as being a near optimal fractional matching in G prime. Hence, the size of M prime is very close to size of W prime. And the sparsification step ensures that size of W prime is very close to size of W. So the size of M prime, the output is very close to the size of W, the fractional matching we started from. This is how a rounding scheme works. Again, for the non-bipartite case, we can deal with it with a little bit of extra effort. Please ignore this for the rest of the talk. Now, since the Gupta-Peng algorithm is running on a sparsifier and the sparsifier has bounded degree, its update time is small, polylogarithmic. So overall, this scheme runs in polylogarithmic update time if you get a fast dynamic sparsification algorithm. Now, how to sparsify? Well, to get the main idea, again, look at a specific instance, dynamic instance, where the graph remains almost D-regular. And let's say D again is some polynomial in n, root n. And suppose in the input to the sparsification algorithm, the fractional matching we get is such that it has weight 1 over D for every edge. Let's see what to do in this setting. Now, if you stare at this problem for 5 minutes, the first idea that will hit you is that you can do random sampling. So you can sample each edge into your sparsifier with probability log n over D. And if you do this, what is happening is you look at the output graph G prime. The degrees of the nodes in this output graph G prime is going to get scaled down by your sampling probability. And you just get a fractional matching. You can define as fractional matching W prime in this output graph by setting a weight of 1 over log n to every edge in the output graph. So essentially what we are doing is we are scaling the degrees of the nodes by a factor of log n over D. This holds with high probability by Chernoff bounds. On the other hand, we are scaling up the weights of the surviving edges, the sampled edges, by the inverse factor, D over log n. And as a result, the total weight received by the nodes are preserved, again with high probability. And this is a good sparsification scheme, dynamic sparsification scheme. Now this applies only for this very specific input instance. What RR et al. In 2018 showed was that you can make it work on general input instances. So they showed how to do dynamic sparsification via independent random sampling. However, it works only against oblivious adversary. Subsequently, last year, David Wise came up with a very clever randomized algorithm for dynamic sparsification that works against an adaptive adversary, but it's still randomized. Okay, so now we are ready to precisely define our result. Let's look at the common template for dynamic matching. The first ingredient is a dynamic fractional matching algorithm that outputs a fractional matching. The second ingredient is a dynamic sparsification algorithm that will sparsify this fractional matching and output a sparse subgraph G prime that preserves the size of the fractional matching. Finally, you feed this sparsifier into a dynamic matching algorithm that runs very well on sparse graphs. And you output what you get out of this last subroutine, M prime. So this is the overall framework. And we just discussed that the dynamic sparsification algorithms that we know of are randomized. And we also discussed some time back that these two other ingredients, the fractional matching algorithms and the dynamic matching algorithms for sparse graphs, they are all deterministic. Now, our contribution is to de-randomize the dynamic sparsification step. So we give a deterministic algorithm for dynamic sparsification. And that means that this second step now can be done in a deterministic manner. And as a result, all these three steps are now deterministic. And as an immediate corollary, we get multiple new deterministic algorithms for dynamic matching. Okay, so the specific implications of our result are the following new deterministic algorithms in the following settings: a 1 plus epsilon approximation in decremental bipartite graphs in polylog update time, slightly better than 2 approximation in fully dynamic bipartite graphs in n to the power epsilon update time, and 2 plus epsilon approximation in fully dynamic general graphs in small polylogarithmic log to the power 4n update times. But again, the main conceptual message behind the paper is that we can do dynamic sparsification of matchings deterministically. That's the main message. And these results are corollaries of that message. Okay, so now we are roughly at the halfway mark of the talk. And from this point onward, I'm going to discuss our techniques. And as usual, if you have any question, please feel free to use the chat. Okay, so our techniques. What is the main challenge? The main challenge was the dynamic sparsification algorithm. So let's precisely define this setting now. So the input is a dynamic graph and a fractional matching W. So specifically, okay, just one question. Ramanujan, can you see my cursor if I'm moving my cursor?
Yes, I can see that.
Oh, Igor, you can see that, right? Yeah, okay, thanks. Okay, so the specific setting is this. The input is a dynamic graph and a fractional matching W. And the updates are you are inserting and deleting an edge in the graph, or you are changing the weight of an edge in E. That's the input. That's the updates. And the dynamic sparsification algorithm is supposed to output a sparse subgraph that preserves the size of the matching W. And we want it deterministic. Now, first, let's get a simple thing out of the way. It's a standard thing, but note that it's okay to assume that the input matching W is uniform, that W of E is lambda for every edge E in the input graph. Why? If it is not uniform, okay, And if this claim is true, what does this mean when we are talking about the update to this sparsification algorithm? The update is just insert or delete an edge in the graph, because the weights of all the edges are unchanged. They are fixed. They are lambda. Why we can make this assumption? It's because we can just discretize the input matching W into log n groups in powers of epsilon. Basically, EI will be the set of edges whose weights are 1 plus epsilon to the power minus I. And this partitions the input graph into these log n different subgraphs. And in each subgraph, you now have a uniform fractional matching. And you can sparsify each of them individually, and then you can take the union of them. And you can do everything here in the dynamic setting. So I'm just leaving the technical details, but conceptually it should be easy to appreciate that we can make this assumption. So from this point onward, we are going to assume that W is uniform. And we will say that this fractional matching W is lambda uniform because lambda is a parameter. Every weight is equal to lambda. Now, our main challenge is to design a deterministic dynamic algorithm for sparsifying a lambda uniform fractional matching. Now, for quite some time, maybe for the next 10-15 minutes, I'll be talking about a static algorithm for sparsifying a uniform fractional matching. And if we understand clearly what is going on in the static algorithm, and this is one algorithm we design, if we understand this first, that making it dynamic will be conceptually relatively natural and straightforward. So what is the static algorithm? And here is the main idea. The main idea is a degree split subroutine. So it takes as input this graph G. It runs in linear time in the number of edges in the graph, and it outputs a subgraph G prime, which has the following property. Every node in this subgraph has its degree halved. So for every node V, its degree in G prime is very close to its degree in the original graph divided by 2. That's why we call it the degree split subroutine. And if we have this, then we can define a new matching W prime in this output subgraph G prime that is 2 lambda uniform. So recall that initially we started with a lambda uniform fractional matching W. And now we are splitting the degrees, getting the resulting subgraph E prime. And we are basically doubling the weight of every edge in E prime. And if we do that, we will see that the weights of the nodes are preserved. And what is going on is actually very simple. So consider this node V. It has 6 edges incident on it in G. Its total weight was 6 lambda. The degree split subroutine will output a subgraph G prime, where this node will have degree 3. And these surviving edges in E prime, we will double their weights. So the weight of the node V in this new matching will still remain 6 lambda. It's equal to its old weight. That's all that is going on. Now, what is the size of a fractional matching? By a simple counting argument, it's just half times the sum of the node weights. So after degree split, the node weights are preserved. It just means that the size of the fractional matching W is also preserved. So size of W prime is roughly the same as the size of W. Okay. This is the output of degree split. And now, again, I am stuck. This is very annoying. Okay. Now, yeah, now let me again start from here. Okay, so this is where we are. And note one other thing. What happens to the maximum degree of the graph? The maximum degree of G prime is basically half times the maximum degree of G. Why? Because every node's degree is being halved. Okay, now that we have this degree split subroutine, how can we use this for our sparsification in the static setting. Basically, we will repeatedly apply degree split log n many times. So we start with this graph G and the fractional matching W. We apply one round of degree split. We get a subgraph G1 and a fractional matching W1. Give me 1 second. I think it's better. Okay. Okay. And now we get this G1, W1 out of first round of degree splitting. We feed it into our second round of degree split. And we keep doing this for log n rounds. In the end, we get G log n and a fractional matching W log n. What can we say about the maximum degree in G log n? Well, after every round of degree split, the max degree got halved. Initially, maybe the max degree was n. So after log n rounds, the max degree is constant. And after every round of degree split, the size of the fractional matching was approximately preserved. So the size of W log n is roughly the same as the size of W. So this is the output of our sparsification algorithm. Okay. Okay, sorry, I'm having some trouble with my laptop. Okay, so we can return G log n and W log n. And what is the total runtime? Basically, each round of degree split runs in linear time in the number of edges in the input graph. And hence, the total runtime will be the sum of the sizes of these EIs. And these sizes of these EIs keep getting halved. Why? Because the degrees keep getting halved. So this forms a geometric series, and hence the total runtime remains order of E. So this is linear total running time. Now, how to apply this degree splitting idea? Give me 1 second. Again. Okay, I need to share my screen again. Okay, is the screen share working now?
Yes.
Okay, sorry. So you return, thanks, G log n, W log n. And so this is how it works in the static setting. Now let's look at the degree split subroutine for a uniform fractional matching. And the degree split subroutine works as follows. I really don't understand what is going on.
Sayan, maybe if you could, if it's better with the non-full screen one, with the thumbnails on the left, I suppose that's
no,
okay.
I think this is fine. Let's just do it this way. If it gets stuck for 2-3 more times, I will just switch back to this thing. Thanks.
Sure.
Okay. So now moving on, let's just look at this degree split subroutine. And it will be implemented as follows. We partition the edge set E into a set of disjoint maximal walks. And now for each walk, we collect alternate edges from these walks. And then we let E prime denote the unions of these subsets Wi stars. And we just return G prime to be V comma E prime and a 2 lambda uniform fractional matching W prime on E prime. Let me illustrate this by means of a picture. Suppose this is our input graph. You start an arbitrary walk from a node W1. And I will just color alternate edges of this walk using dashed red and solid red. So this is how the walk is proceeding. And now we are stuck. We have reached V1 and we cannot proceed any further. So we complete this walk now. This is going to be our first walk, W1. And W1 star will be alternate edges from this walk. So W1 star will be just the solid red edges in this walk. Whereas W1 is the dotted red edges and the solid red edges. We now remove these edges in W1 from the graph G, and we start another walk from V5, let's say. And now I'm going to color the alternate edges in this walk using dashed blue and solid blue. And I keep doing this. And now I get stuck again at V4. And this is going to be our second walk, W2. And when we are collecting alternate edges in this walk, let's collect only the solid edges, and that will be W2 star. So now E prime will be W1 star union W2 star. So these will be just the solid red edges and the solid blue edges. And this will give us the graph G prime. And note that the runtime of this entire procedure is linear in the number of edges, because we are just partitioning the graph G into disjoint maximal walks. So this runs in linear time. And it actually does degree splitting very well. If you stare at it for 5 minutes, you will realize what is happening is it will split the degrees of all the even degree nodes exactly by half. And for the odd degree nodes, their degree in the resulting output, G prime, will be off from their initial degree by at most an additive 1 factor. So for all nodes V, the degree in the output is plus minus 1 of half times its degree in the initial graph. So that's the claim, and it's easy to verify this claim. Now, we actually wanted the degrees to be within 1 plus minus epsilon factor of half times the original degrees. But here we get actually a plus minus 1 additive factor. So there is a difference between what we actually want and what this claim gives us. And this essentially means that we are fine as long as every node in this graph has degree at least 1 over epsilon, because then these two claims are equivalent. A plus minus 1 additive approximation gives a 1 plus minus epsilon multiplicative approximation. But we will get stuck when there are nodes in this graph with small degrees. Their degrees we cannot split very evenly. And this is now the main technical challenge. And we incorporate this technical challenge by modifying our degree split subroutine as follows. Step 1, we repeatedly keep removing nodes with small degree from the graph. Step 2, once step 1 is over, look at the resulting graph G star, where no more nodes can be removed. And step 3, apply the original degree split subroutine on G star. So pictorially, it looks like this. Let V1, V2, Vi, ... Vk be the nodes we removed in successive iterations of step 1. So V1 was the node that got removed in the first iteration of step 1. V2 is the node that got removed in the second iteration of step 1, and so on. And G star is the remaining graph we end up with when step 1 is over. So of course, the node set V is partitioned into V star and V1 to Vk, and G star is the subgraph of G induced by V star. First thing to note is that the minimum degree in G star is by definition at least 1 over epsilon, because otherwise we would have not stopped step 1. And since min degree in G star is large, we can apply original degree split on G star. Now, here is one other thing. Look at a node look at the node Vi that got removed in the ith iteration of step 1. And look at the edges it has towards its right, towards this set V greater than I, as I have depicted in this figure. It's easy to observe that the degree, the number of neighbors Vi has to the set V greater than I has to be less than 1 over epsilon, because this is precisely the reason why we removed the node Vi during the ith iteration of step 1. This is the reason why it got removed. And in particular, we will refer to these green edges as the frozen edges. It will be clear in a moment why. And let capital F denote the set of all frozen edges across all these K nodes that got removed in step 1. And note that the entire edge set E is partitioned into the frozen edges and the edges in E star. Now, since each node Vi has at most 1 over epsilon many edges going towards its right, it means that the set of edges F admits an orientation with maximum out degree at most 1 over epsilon. So if we just assign a direction to these green edges from left to right, each node will have an out degree that is at most 1 over epsilon. And this is another way of saying that the H set F has arboricity at most order 1 over epsilon. That's the definition of arboricity. And what it is saying is that this H set F is locally sparse. So an example of a locally sparse graph is a star graph. So here you have this star graph with center U and these nodes U1 to UN. If you assign a direction out of U to every edge, the directions should be flipped. If you assign a direction into U, you will notice that this admits an orientation with maximum out degree at most 1. And hence this star graph is actually locally sparse, although it has large maximum degree. So this is the takeaway message from this picture, that the set of frozen edges has low arboricity. And now we are in step 3. In step 3, we will take this graph G star, apply our original degree split subroutine, which works just fine because G star has large minimum degree. And let the output of the original degree split subroutine on G star be denoted by G prime, colored in red, and we will refer to the red edges as surviving edges. They are surviving the degree split. And what we will return as the output of our modified degree split algorithm is the union of the red edges, the surviving edges, and the green edges, the frozen edges. And we will return a fractional matching WH, which is defined as follows. The green edges, their weights remain the same as before. That's why we call them frozen, because their weights get frozen. And the red edges, we double their weights just as before. Just as in original degree split, the output of that subroutine's edges double their weights. The same thing is happening here. And if you stare at this entire slide for a while, you will realize that the output fractional matching again has this nice property that it preserves the weights of every node because of the property of the degree split, that it's preserving the weights of every node, and the frozen edges, their weights remain unchanged. Okay. And the entire scheme here can be implemented in linear time because step 1, repeatedly removing nodes, that can be implemented in linear time, and step 3, degree split, can also be implemented in linear time. And now here is the static sparsification algorithm. We just keep repeatedly applying degree split log n times. So after first iteration, we get a bunch of frozen edges F1, and the remaining surviving edges go to G1. The frozen edges, their weights get frozen to their initial value. The surviving edges, their weights get doubled. And we keep doing this. We keep doing this log n many times. And ultimately, what we return is the subgraph H consisting of all the frozen edges and the final leftover surviving edges, that is E log n. And the fractional matching WH, the way we described in the previous slide. That's the output. And as we discussed, this will preserve the property that the node weights are preserved in the output fractional matching. And this means that the size of the output fractional matching is very close to the size of the initial fractional matching. And finally, each of these sets, frozen sets, F1, F2 until F log n, has arboricity 1 over epsilon. So their union will have arboricity at most log n over epsilon. So the output graph H is also locally sparse. It has small arboricity. And the total runtime, we are doing this log n times, but after each round, the number of edges keep getting halved. We get a geometric series. The total runtime is still linear. So now, in the next 5 minutes, I will just show how to make this entire thing dynamic. But first, let's just quickly recap. Let's quickly give a summary of what we did. We gave a static sparsification algorithm that is deterministic, which outputs a sparse subgraph with small arboricity and which preserves the size of the input fractional matching. So these three things are written down here, and this runs in linear time. Our challenge will be to make it dynamic. We will see in 5 minutes how to do this. But once we make it dynamic, we can actually feed it into an algorithm by Peleg and Solomon for maintaining dynamic matching on low arboricity graphs. And this will output a near optimal matching M. The update time will be proportional to the arboricity, which is log n over epsilon, and we are all good. So this is the overall framework. Finally, I'm left with 5 minutes. I'll just try to explain how to make it dynamic. So everything we discussed until now was in the static setting. The main idea in the dynamic setting is to be lazy. So we take this structure that we get out of the static algorithm. We now process the insertions and deletions of the edges in G, and we process them as lazily as we can. So handling edge insertions, suppose initially we have M edges. The input fractional matching is lambda uniform. Its size is lambda M. Our output fractional matching also has size close to lambda M. When an edge gets inserted, we just ignore the insertion. We pretend it doesn't exist. And we keep doing this until epsilon M many edges get inserted. At this point, the size of the input fractional matching has increased by 1 plus epsilon factor. But the matching that we are maintaining remains the same as before. So we are still preserving our approximation guarantee. We are not too far off from the input matching. And now we rebuild everything from scratch. And when we are rebuilding everything from scratch, what will be our amortized update time? The time taken for rebuilding everything from scratch is just linear in the number of edges. This is M, but we waited for epsilon M many edge insertions. So this is the amortized update time, M divided by epsilon M, which is 1 over epsilon. For handling edge deletions, initially we have, again, let's say M edges, size of the input matching is lambda times M, size of our output fractional matching is lambda times M. When an edge E gets deleted, we remove E from this structure, from our output H, and set the weight of this removed edge to 0 so that it does not contribute anything to the weights of the nodes. So we are just trying to be lazy and be correct as long as possible. That's our motto. And we keep doing this until the size of our output fractional matching drops by 1 minus epsilon factor because maybe too many edges got deleted. At that point, by a simple counting argument, we can identify a critical round I from 1 to log n such that the input to that round, the set of edges input to that round, this is EI, their size has dropped by at least 1 minus epsilon log n factor. And this is a counting argument. It just says if our output fractional matching has dropped sufficiently, there must be one round where the input EI has shrinked sufficiently. So we identify that critical round I. And now we just rebuild all the rounds j greater than or equal to I, all the rounds from I and above from scratch. And what will be the time taken for rebuild? It's again going to be linear in the size of EI, because remember, these rounds basically geometrically decreases the sizes of the matchings. So the rebuild time is proportional to EI, but we did this rebuild after epsilon log n fraction of the edges from EI got deleted. So our amortized update time is just log n over epsilon, and we are happy. And finally, the size of our output fractional matching keeps remaining close to the size of the input fractional matching, because informally, we continue to remain close to the output of the static algorithm. That's the intuition. Now, we need to do a lot of math to formally prove everything and put things together. But I hope I managed to convey the overall picture, the main idea behind the algorithm to you. And now, let me quickly conclude the talk. In 2 lines, here is the summary of our contributions. So we present an efficient deterministic near lossless rounding scheme for dynamic fractional matchings. And as a corollary, we obtain multiple new deterministic dynamic matching algorithms in various settings. That's the summary. And finally, one interesting observation, our algorithm uses the Pelec-Solomon dynamic matching algorithm on bounded arboricity graphs as a black box subroutine. And this just means that if we manage to give good dynamic matching algorithms on bounded arboricity graphs, then we can boost them up to actually convert them into good dynamic matching algorithm on general graphs. And I find this message conceptually very intriguing, that if you can solve dynamic matching on bounded arboricity graphs, you can solve them on general graphs. Okay, so this is the conclusion. And thanks for attending the talk. I'll be very happy to take any questions.
Thanks, Sayan, for the very nice talk. So are there any questions for Sayan?
Thanks, Sayan. This talk was really excellent. It was very clear. So I'm curious about something you mentioned in the middle of the talk. Like you said something about the part of randomness in this setting of fully dynamic algorithms.
Mm-hmm.
And I think you said that there is no conditional separation.
Yes, let me just go back to that.
Yeah,
slide.
sure.
Give me 1 second.
Mm-hmm.
Are you
Yeah,
too afraid to
this was the
share it
slide,
again?
right? Can you? Oh, can you see my screen?
No, I cannot see your screen.
Oh, okay. 1 second. Can you see the screen?
Now, yes.
Yes. Yes. So my question, when you said that there is no conditional separation, is this particular to the matching problem or a general
No,
situation?
This is true in general for dynamic problems, because there are currently only two ways to prove dynamic lower bounds. One is self-prove lower bounds, unconditional, information theoretic, using communication complexity, those kind of tools. But using them, we don't know how to prove super polylogarithmic lower bound. It will be a huge result if anybody manages to do that. The second one is conditional lower bounds. Let's say using ACTH, you assume ACTH and then show that you cannot do dynamic matching faster than this. But then ACTH is a stacking problem. So the lower bound you get applies also in the offline setting. So basically the adversary has written down the updates on a piece of paper. You can go through these updates. You can go back and forth as many times as you want, but for each update step, you need to output the answer. And also for ACTH, the starting conjecture itself cannot distinguish between deterministic versus randomized.
Right.
So for conditional lower bounds, we first need to start with a conjecture which is easy using randomization, but hard.
Yeah, and that's not gonna happen probably, I guess.
Yes.
So, okay, I see. Thanks a lot.
Yeah. Thanks.
Sayan, any more questions? I had a probably simple one. So in this talk, in the beginning, you mentioned that you're going to assume that you're working on bipartite graphs. So where exactly was this used?
Oh, so in this, let me actually, no, this is not the thing. Let me just dig up this. Yeah, I think this is the part. Okay. So it was used here. So look at this third ingredient, dynamic matching algorithm for sparse graphs. This gives you 1 plus epsilon approximate integral matching. Now, in a bipartite graph, there is no gap between fractional versus integral. So if you are feeding it a fractional matching of value lambda, this third ingredient will output you an integral matching of value 1 minus epsilon times lambda.
I see. Okay.
But for general graphs, it's not going to be true. And there we use properties of the existing fractional matching algorithms to show that if you have a certain kind of fractional matching algorithm which gives two approximation, even on general graphs, you don't lose any extra 3½ factor. when you are making this conversion from fractional to integral.
Okay, and this additional requirements on this premise, are these very complex?
No, so the actual statement is very complex, but I can just give you the intuition in just 1 minute. The intuition is this: take a d-regular general graph, exactly d-regular general graph. This is non-bipartite, but does it admit an integrality gap of 3/2? The answer is no. Why? Because if d is large enough, let's say d is root n, it's a d-regular general graph. By Weising's theorem, it admits a d+1 edge coloring. Color those edges, and then by a simple averaging argument, one color class will be of size that is 1 over d+1 times the total size of the matching. And that is almost nearly as good as you are going to get with the fractional matching. And this is the property that these dynamic fractional matching algorithms utilize, provided you are shooting for 2 approximation.
Let's see. Okay. Thanks, Sean. That helps. Any other questions for Sean? Okay, if not, let's start. Thanks, Sean, again. Congratulations to Sean and Peter again.
Oh, thanks a lot. Thanks.
Thanks.
Hope to see you all next week.
Yeah. Bye.
Bye-bye.
Thank you, Sayan.
Thanks.